Syzygy, Episode 3, NASA is all go and Emily is all fingers crossed for TESS. Hello and welcome to another episode of Syzygy. I'm Chris Stewart, and joining me at the microphone, as ever, is University of York astronomer Dr Emily Brunsden. Hi, Emily.
Hello, hello.
Now, today is a very big day. I'm looking at you across the table from me here, and you just got this look on your face, which is, it's exciting because today is all about TESS. We're waiting for a big launch from NASA, right?
Yes, TESS is going up in its own little rocket today.
Oh, it's so exciting. We've even got on the table in front of us, we've got a little cardboard model of TESS. Where'd that come from?
I put that together. It was based on a guy who contributed the design on the internet.
Very nice. Very nice. We'll put a picture of that in the show notes. But before we get to that, we've had some listener questions, some listener feedback from friend of the show, Graham in Australia. Graham has asked us, based on one of our previous episodes, he said, look, all of this astronomical naming scheme that you've got there, it's all fun and games, but what does it actually mean? And what he's referring to is astronomers' way of naming things in not particularly exciting ways. We talked about a galaxy in one of our previous episodes, which was NGC, and then a whole phone book of numbers. And the question is, why? Where do these naming schemes come from, Emily?
Well, actually, it's quite uninteresting in some senses. Most of the names that we use come from different catalogues. So we'll draw up a list of the objects of a particular type that we see in a sky. Some of these catalogues can be quite old. The Messier catalogue, for example, was basically all the smudgy things that Messier saw on the sky. And
so when you hear about things which are Messier objects, Messier object 1473, that's from the Messier catalogue.
Yeah, we tend to call them, they tend to be lower numbers than that because there's only a few of them, but they're usually the biggest, brightest galaxies, and they'll be called like M31, M101, these kind of things.
Right. So the one that we were talking about was NGC something. So what's NGC?
So NGC is very unimaginatively the new general catalogue.
As opposed to the old general catalogue. How new is the new general catalogue?
Well, I just checked this one, and it was put together in about 1888.
Right, so not so new.
Not so new, but basically is a catalogue of mostly galaxies and other similar types of objects.
Right, so the idea being that there's a lot of things up in the sky, and so if you're going to spend your time looking at them and figuring out something about them, you need to, at some point, write down all the details. And after you've gone through Mercury, Venus, Earth, Mars, we can give names to these things where the galaxy across the sky, it looks like a big smudge of milk. We'll call it the Milky Way. Okay, we're running out of names. We just need to give them numbers. And so just start writing down in our catalogue of objects numbers against the things that we see, and that becomes their name.
Exactly, yep. And lots of objects will have many, sometimes dozens of different catalogue numbers depending on which catalogue they put together at the time.
And presumably some things in the sky start off as, as you said before, the Messier objects. Well, that smudge there, that's smudge number 14 in our catalogue, and resolves later on to be, it's not a smudge, that's a galaxy, or that's a nebula, or that's a whatever it might be, as we learn more about them.
Yeah, so we do find that some different types of objects might share the same catalogue in the end.
Well, we could probably spend an entire episode talking about numbering schemes in astronomy, but we're not going to, at least not yet. Not until we run out of topics to cover in this podcast, which I hope is going to be a really long time. If we ever get to that show, I think it's probably time to pull the plug on the podcast. No, let's get to something much more interesting. Let's have a little bit of a talk about TESS. TESS is currently strapped on top of an enormous amount of highly explosive rocket fuel over on a launch pad at SpaceX Central, waiting to take off on a very large rocket tonight at about 6:30 p.m. Eastern American time. Emily, what or who? No?
No, 6:30 p.m. UK time.
Oh, 6:30 p.m. UK time. Is that right?
No, sorry. Oh, no. Oh
no, I was right.
You were right.
I was right. Yeah, 6:30 p.m. Eastern American time. No. Because if we're going to watch that here in the UK, then we're going to be up very late. That's going to be like 11:30 at night.
Yep.
But totally worth it. Totally worth it. Yeah. We're going to be there. We're going to be watching it on NASA TV. But Emily, who or what is TESS?
Well, we can start off with the name.
Okay.
As is so often the case in astronomy, it's a very fun little acronym. So TESS...
At least it has a name. At least it's not sort of, Rocket Part 1479B.
No. We've actually gone for a relatively nice name.
Yeah.
TESS is quite nice. And it does stand for something quite nice as well. It's called the Transiting Exoplanet Survey Satellite.
Okay. Now, we did a bit about exoplanets way back in episode number 1, and we're only at episode number 3. This isn't going to become the Exoplanet podcast, but given the timing of this, we just had to do an episode on it. So the Transient Exoplanet
Survey
Satellite.
Yep.
All right, let's work our way through that one thing. Remind us what transient exoplanets are.
So this is referring to the technique that we're going to use to detect the exoplanets. So it was the same technique that Kepler Space Telescope used. And the idea is that you can look at a distant star. If you look at it over time, then you might see its brightness go down by just a tiny, tiny little bit. And that happens when a planet is actually crossing between your line of sight and the star in the background. So the planet basically blocks out a little bit of the light, so the star appears just a little bit dimmer.
Okay, so that's the transient exoplanet bit, and then survey satellite. So it's surveying, it's not looking at a single star and waiting.
No.
Come on, planet. It's looking at a lot of stars. And this is the same idea behind the Kepler and the K2 surveys, isn't it? That you're looking at a whole bunch of stars.
Yeah, so we look at lots and lots and lots of stars to get the statistics, basically, of getting lots and lots of different transits.
I seem to remember you saying previously that when things happen very, very rarely, the thing you need to do in astronomy is to look at lots and lots and lots of things.
Yep.
So how many things is TESS going to be looking at?
Oh, just about 200,000 stars.
But it's a little bit different from Kepler, isn't it? Because Kepler was looking at a fairly small part of the sky, relatively, whereas I seem to remember seeing that TESS was looking at a much bigger.
Yeah, well, this is one of the amazing things. So Kepler looked at a very small patch of sky in the constellation of Cygnus and did a fabulous job at looking at 150,000 stars, so not too dissimilar in terms of numbers, over a period of 3.5 years. TESS is completely different in the sense that now we're coming back, we're looking at the entire sky pretty much, and we're going to look at each little patch of sky for about a month and then move on.
Why would you do that in that different way? Why was Kepler only looking at one particular part of the sky, but finding 150,000 stars there? Why doesn't TESS do the same thing? Or conversely, why didn't Kepler look at the whole sky? Why would you do that differently?
Well, it's because they're kind of asking different questions.
Okay.
So the idea with Kepler, when we launched Kepler in 2009, we didn't really know what were the population statistics of planets in our galaxy. How many actually are there in our galaxy? Do they only go around some particular types of stars? Do they go around all stars? We didn't really know much information about exoplanets at that time at all. So we chose a bit of sky. It's mostly got quite faint stars. Kepler's quite a big telescope, so you can't look at things that are too bright. And there was just a nice range of all the different types of stars that you can have in that field. So we found, of course, that we had all these exoplanets, thousands and thousands of them from Kepler. And now with TESS, we're now asking the question, okay, we know that exoplanets are kind of common now. Maybe every star roughly has one on average. So can we find the ones that are close to us here on Earth? So we need to do that. We need to look at bright stars.
Right. So that's the main difference then, that TESS is looking at bright stars closer to us, but all over the sky, wherever they might be.
Yeah. And there's good reasons for that as well, because we want to be able to get more information out of these exoplanets. With the Kepler stars, they were often very, very faint stars and very difficult then to do follow-up observations from the ground, particularly, and if we want to do other techniques. So with TESS, it's kind of the opposite. You've got all the bright stars in the sky. You're spoilt for choice with telescopes around the world that you can then use to follow up these observations.
So that's the idea then, that TESS gets to go and find, hey, look, there's a star over here. We saw a transit. There's an exoplanet there. Now go and use these other ground-based telescopes to go and have a look at that. Now that we've found it, we've done the hard work. You go and do the fun job of really having a look at this thing. That's the idea?
Yeah, and we can use completely different techniques on bright stars and get much, much more information than we could have on many of the Kepler planets that we found.
So what sort of things would the other telescopes be trying to do and follow up then? You know, you've found the exoplanet. What are they then looking for?
So once you've found an exoplanet, the next question is it going to be suitable for life? And if you want to answer that question, you need to have a lot more data and you need to know some very specific things. What we'd really like to know is more information about the atmosphere of the planet itself. Does it have carbon, carbon dioxide, water in its atmosphere, those kind of things?
How do you tell about the atmosphere of a planet which is around an entirely other star? Like, I can imagine looking at Venus and being able to figure out, okay, so Venus has got a whole bunch of really nasty gases on the surface of it that would dissolve us instantly. I could, because it's just there, you know, it's the next planet over. How do you work out about atmospheres around planets around entirely distant stars, particularly as you're looking for the planet's effect on the brightness of the star in order to be able to see that it's there? You're looking for its transit across the star, that dip in brightness. How do you see what it's made of?
Well, it's fascinating, really.
I knew it would be. That's why I asked.
It's so exciting that we can actually do this. And we have done this for a few exoplanets already. And what we're able to do is, if we point a telescope, if we have an instrument called a spectrograph, then we're able to break up the light from a star. And we look for basically a chemical fingerprint. And this tells you what that star is made of.
So a spectrograph breaks up the light that you can see into its constituent frequencies. You know, if you think about visible light, it's the Roy G. Biv. It's the red, orange, yellow, green, blue, indigo, violet are all the different frequencies that we have in visible light. And then you've got all the other frequencies as well, infrared and ultraviolet and so on. So you can break up the light from the star into those different colors of light, if you like, or those different frequencies of light, in order to see these chemical signatures, which you infer back to the planet.
Well, you can start off with the star and you can work out what's going on the surface of the star.
Okay.
And what kind of species are there, lots of hydrogen, helium, that kind of thing. And then when the planet is going in front of the star, some of the light that we get in our telescopes has been through the atmosphere of the planet itself.
That's clever.
It's
clever.
Very nice.
So you figure out what's there in the starlight to begin with, and then you see how that changes. So, wow. So you're looking at such an incredibly small dip in the brightness of the star as this planet goes across in front of it anyway. But not only that, you're able to actually infer from that chemicals in the atmosphere of the planet itself, just from how that chemical signature of the starlight changes.
Yeah, it's an amazing technique.
That's bonkers.
It's really,
Sorry,
really
but
cool.
It is.
But it works, and we've got a couple of examples where we've got this, and But the problem is that when you take the light and break it up into colours, you need to have a lot of light to be able to do that. So it's incredibly difficult to do with very, very faint stars.
Hence the need for really bright ones nearby. So what sort of things can you see when you look at those atmospheres? What kind of chemicals are they looking for?
Well, they've found lots of different signatures of things like water, carbon dioxide, and these kind of ordinary atmospheric gases. When you talk about the search for life, what you're looking for is a disequilibrium effect. So when you think about the Earth, then we've put our own atmosphere out of equilibrium position because we have living organisms that are changing, basically, the chemical composition. So you're looking for those kinds of changes.
Now, you're not just talking about the fact that humans are currently messing up the atmosphere of our planet big time. You're not talking about that kind of out of equilibrium. You're just talking about living things changing what otherwise would be a nice, simple equilibrium within the atmosphere, with things like, oxygen cycles and carbon cycles and that sort of thing. Yeah,
even very basic algae will change the atmosphere of the planet that they're living on, basically. Because if you've got a particular gas that you can't, that's been produced by a living organism, and it would normally sort of drift away, or it would be consumed back into the system, then you know that there must be something that's producing that gas. Now, what those actual gases are is kind of up for debate a little bit, and there's a lot of discussion as to what can be caused by geological processes and what are biological processes.
So it's not just a matter of, hey, look, we saw this particular chemical, therefore life. Obviously, life on that planet. It's a bit more subtle than that.
Yeah, and there's lots of work going on in this area at the moment to work out what those chemicals might be.
Yeah, I mean, it's weird, isn't it, that we have statistically we have an N of 1 as far as life is concerned, with planets with life on them. We know what's in our atmosphere as a result of life on this planet, but that doesn't necessarily tell us what we should be looking for somewhere else. But it at least gives it a place to start. So, I mean, have you astronomer people, have you found these chemical signatures around planets yet?
We've found some chemical signatures. They're not really indicative of life at this point.
Right.
So, yeah, it's what we need really are more data.
Mm-hmm.
So,
hence TESS.
Yeah, exactly.
So other than that, what are the other main science goals of this satellite?
Well, one big thing we're trying to understand with exoplanets is that let's go for the easy ones first, right? So the easiest exoplanets to find are ones that have very short periods. So when you see a transit, then you have to wait a while until it happens again. And when you've, wait a while and you measure the length of time that passes before the next transit, then you know the orbital period of the planet.
And waiting a while, I mean, if you think about it from the point of view of the Earth, it takes a year for us to go around our star. Mercury goes around
88 days.
88 days. And Jupiter takes ages.
Yeah.
Really long periods of time. So, when you say waiting a little while, it could be a really long time for that to happen again.
So we've got to go for the easy ones first.
Yeah,
so we're going for ones that are, in TESS's case, we're looking for planets that are going around basically every 10 days or less.
So that's really close.
Yeah.
Really close to the host star.
Now, if you want to put a planet really close to a host star and you want it to still be kind of viable for life, then you've got to turn down your temperature on your host star, right?
Yeah, because Mercury, no one's moving to Mercury anytime soon. And that's got an orbital period of 88 days. That's not even comparatively close to what you're talking about.
No.
And you wouldn't move there. No. So what kind of star would that have to be? That's got to be a pretty cool star.
Yeah, so these are some of the reddest stars that we have, and not so much in the sky, because there's all sorts of different interesting things that go on with stars throughout their lives.
So, and remembering temperature of star goes with colour, doesn't it?
Yes.
And a little bit paradoxically from what we experience around us in everyday life, red is actually not that hot.
No,
it's the blue ones that are really hot.
Yeah, so our sun's kind of a middle star. Turns out how hot a star is during its normal life is completely dependent on how much mass it has. So our sun is kind of just a normal mass star. It's kind of a yellowy colour, maybe a bit green. And so it's just kind of sitting there in the middle. But there are lots and lots of stars that are much, much smaller and therefore much, much redder. So whilst our sun has a surface temperature of maybe 6,000 Kelvin or 6,000 degrees, it's kind of the same at that point. These stars have temperatures of maybe only 3,000. So
you could have a planet much closer and still be habitable,
Yeah.
whipping around it every 10 days or so. Wow.
Yeah.
That's really cool.
Yeah, so then we know that there's going to be lots and lots of these types of stars. They're actually much more common than stars like our sun. So we expect to find lots of these little planets going around.
So TESS should be able to
These
find a
red
whole bunch
stars.
of those fairly close to us, bright enough. Even though they're cooler, they'll still be bright enough for TESS to be able to see. And with any luck, find some planets nice and close.
Yeah. So kind of like looking for our nearest neighbours, if you like.
Yeah, cool. Okay. So what else is TESS looking for?
So, well, the wonderful thing about TESS is it's just going to be doing a massive sky survey. So it's got 4 cameras on board, and each one's going to be pointing at a bit of the sky. It's quite a big chunk of sky that it's taking in at a time. So it's something like 24 by 24 degrees. If you think about the size of the full moon in the sky, that's only about half a degree.
Right. So
these
that
are
is a big bit of sky.
Big chunks of sky.
Wow.
And it will look at each of those patches of sky for a whole month, uninterrupted. So there's no day-night. It's just pure space observations, basically, for a whole month.
So, it's interesting. If you go and look at an image of the sort of patch of sky that Kepler was looking at, to our eyes, it doesn't look like much because we can't see most of the stars that Kepler can see. But the stars that we can see in the night sky are the bright ones. And with TESS looking at the sky, looking for the bright stars that are fairly close to us, okay, you can probably see a heck of a lot more stars than we can. But it's a little bit more like us looking up at the night sky and seeing the brightest, closest stars.
Yeah. So basically the fainter half of, if you like, of the stars that we see in the sky will be being measured by TESS.
Right. Cool. So you said it's got 4 cameras. Are they all doing the same thing?
So they're looking at 4 different fields at a time.
At once?
Yeah. So over a course of a year, then TESS is going to be able to map out half of the entire sky, which is pretty amazing. It's a big sky. And then after a year, it's going to flip around and do the other hemisphere.
And do the other half?
Yeah. And hopefully, if it's still going after those 2 years, then we'll continue and go back and
start again.
Yeah, do some more.
How long is it looking at each area of sky?
So each is about a month. So if you think about looking for something that has a period of about 10 days, then that's kind of about right.
You might get a couple of repeats in there, 2 and then 1 extra one, just to make absolutely sure. What are the shortest time frames over? Like, what's the shortest period that we've seen a planet going around a star?
Oh, it's only a few days.
Right.
So, yeah, they can whip around really, really quickly.
Right.
But
then you might also see a whole bunch where you just see one.
There'll be lots of those.
Yeah.
And they will be a little bit frustrating.
Yeah.
But we can always go follow any individual stars up that are quite interesting.
Yeah. I mean, presumably, if our solar system is anything to go by, most of them will be considerably longer than a month. So I would have thought but then that's me saying our solar system is normal, isn't it? So,
But then also it's very unlikely that you're going to see a transit from our solar system or a similar type of system because the alignment would have to be just right for that point in the orbit, if that makes sense.
Hang on. Back up there a second. Why is it more likely?
So if you think about the Earth,
Yeah.
if you're only observing the sun from another star system and you're only observing it for a month, the chances are that the Earth goes across it are fairly small.
Right.
1 in 12, right? And then you've got to consider the alignment issue. So you have to be aligned such that the planet's really going to go in front of the star from your perspective. Because if it goes above or below, then you're just not going to know it's there.
So are you saying that having planets much closer in orbit to the star, you're much more likely to see it? Is that the point you're making? That if you've got something really in close whipping around, not only do you have a higher chance of seeing it more often because it's going around much faster, but that because it's closer, you've got a better chance of actually seeing it crossing in front of the star at all. Yeah, that
and
makes
it's going to
sense.
make a bigger shadow, if you like, on the star, so it's going to have a bigger effect on the light curve. And they're just generally easier.
How is TESS looking? What kind of cameras are these? Is this visible that it's looking in? Is it looking in infrared, ultraviolet, X-ray? What's it doing?
We call it optical, but the wavelengths, if you like, or the colours that TESS is looking at are shifted towards the red because we are looking at more of these cool stars. So again, Kepler sort of looked at it basically across the entire visible range. TESS is a little bit more geared towards the red stars.
So, I mean, it's in the name, right? Transit Exoplanet Sky Survey. So it's all about the exoplanets. But are there any other scientific goals that it's got on its mission? Is TESS going to be looking for anything else?
Of course. Of course. Well, as soon as you start putting up a particular type of observatory or telescope, then everyone starts to think, oh, how can I possibly use
Everyone
that?
wants a piece of that.
And the wonderful thing about these surveys is that there are lots of different types of astronomy that benefit from surveys. So I work in variable stars, and we're very interested in how the light of a star changes over time, not because it's got a planet, but because the star itself is changing. And there are surface changes on the star that are periodic and regular that we can monitor. And so having a spacecraft point at a star for a month uninterrupted is perfect for us, really.
Yeah, we'll take some of that data.
Yeah,
Thanks very much.
Exactly. There's lots of other areas that are interested in new objects or novae. So if a star, even if there is a supernova in a very distant system, that can be bright enough to trigger detections in TESS. So there's lots of areas of astronomy where these kind of data are really useful, actually.
It's got to be a lot of data. I'm imagining TESS is got a pretty thick cable hanging down to some computers down on Earth. I mean, there's a lot of data being thrown back. If you're looking for a month per camera, enormous numbers of stars are changing.
Yeah. So
that's a hell of a lot of data.
And it's even bigger, really, than that that number kind of tells you, because the 200,000 stars, these are just the stars that we call short cadence, which means that we're looking at an image from them every 2 minutes. So 2 minutes passes, TESS takes an image, etc., etc. And that's huge numbers of images over a month, even just in one field. And then what's also happening is TESS takes an image of the entire field of view, just like a picture, and downloads that every 30 minutes. So we're going to have screens of data. So part of TESS's orbit is designed so that it comes quite close to the Earth, just so that it can download basically all these enormous amounts of data and then carry along. So it's a little bit shorter than a month. It's each observing cycle, just to have time to download all the data from each camera.
What kind of orbit is it on?
Well, it's a new kind of orbit, which is really exciting as well. So as often we put telescopes quite a way away from the Earth to get away from Earth shine or the light of Earth itself.
All our noise as well.
Yeah, but this one is quite close. So Hubble is quite close to the Earth, for example. But TESS is a little bit different. It's kind of a high Earth orbit where it's in resonance with the moon. So we're using the moon's gravity to help stabilize the orbit of TESS.
Cool.
Yeah, it's really quite nice.
Nice one.
Yeah, so it's about half the orbit of the moon. So TESS will go around every 13.7-ish days, which is roughly half of the moon's orbit. And it goes out to nearly the orbit of the moon and comes back. And so it's not a circle like the moon's orbit. It's a bit of an ellipse.
And then, as you say, every once in a while comes in nice and close to be able to just throw a whole pile of data and say, quick, go and have a look at this. I mean, that's one of the fascinating things about modern astronomy, isn't it? Is that, in a way, through modern telescopes like this one, you're getting more data than we know what to do with at this point, and you're not going to sort of say, oh no, let's not put TESS up because no, we need to sift through all of this other stuff first. No, by all means, put up the telescope. Let's start bringing in more data. But there are just reams of data waiting still to be analysed for so many different things. I'm guessing TESS is going to be giving us all sorts of stuff that it's going to take us years to sift through.
Exactly, yeah. And it's very, very exciting. And the data are public as well. So anyone can hook into the data from these big missions and actually have a look at it, which expands the science. So it's good for everybody.
Now, of course, you're talking about this in the present tense. Of course, TESS is up there. It's doing its thing. It's sending the data. No, it's not. This thing hasn't even launched yet. Are you nervous?
A little bit, but I have to just think, well, there are people whose professional lives have been working up towards things like this.
Yeah, so. I mean, this is SpaceX, and they did manage to put, a dummy in a bright red car on its way to Mars. So I think we, fingers crossed they can do, proper scientific instruments as well. We'll just have to see what happens tonight. But I guess, can we take a step back and take a slightly broader view of all of this? What's I guess in a sense, the question that you often come back to in astronomy is why do we care? What's the human benefit of TESS and gathering all of this data? What are we going to learn from doing this?
Well, yeah, it's a really good question. I think TESS is quite an easy one for people to engage with because we're talking about exoplanets, which is exciting. We're thinking about, is there life in the universe apart from ourselves? And that's a really interesting and captivating question.
If we do find evidence of life, it's probably not going to be in the form of a coded message coming from one part of the sky. It feels to me much more likely that we would see evidence for life of the kind that you're talking about, which is, we're looking at this planet going around another star and we can see in its atmosphere signs of life. And that might be that it's just, microbes. But it's there.
Yeah. So I think what's interesting about these missions too is that the impact that it has on individuals as well. So when we think about a telescope going up, of course there have been scientists working on this. TESS was originally proposed in about 2006. So it's been around, the idea has been around for a while. People have been working on this for a decade, basically.
Yeah, more.
But that's kind of the professional side of things. And you kind of expect that from people who work on telescopes. Fine. I think what sometimes it's easy to forget is that other people's lives in science are also going to really hinge on this. So if we work our way down through, I guess, kind of the system of academia and come down to people like postdoctoral students, PhD students, there are hundreds, if not even thousands, of people out there whose research work, this is the beginning of their career in terms of postdocs, or even their PhD project is going to be entirely dependent on TESS. And that's quite exciting.
Yeah.
There's so much funding being kicked around to enable these projects to happen. And you think your PhD as a scientist is kind of the defining part of your research. That's often the case of what you're going to research for the rest of your career.
So to be coming on board now, as you say, there's an entire ecosystem of academia just waiting for that.
Yeah.
Hundreds, thousands of people all over the world.
So from lots of these students, particularly PhDs, the biggest thing that they're going to do in their lives, their big PhD, is going to take 3-4 years. It's going to be based off this mission, which is really exciting, I think.
That's really cool.
Obviously, missions like this are really important for talking about inspiring people into science, inspiring people who are non-traditional backgrounds into science. That often means women or people from diverse cultural backgrounds. Those are really important, having these kind of hooks that you can get sparks and excited about. One of the projects with TESS that I found just fascinating was they had a competition, or it's not even really a competition, it was kind of an open call where you could draw a picture of what you thought an exoplanet looked like.
Okay.
And that picture is currently, well, if it was submitted before, I think it was November last year, they took all the pictures, mostly from primary schools children, put them on an SD card, and it's flying on the satellite TESS itself.
That's so cool.
It's really cool.
It's not part of the scientific instrument, but it's there. It's up there in the spaceship. Like that, if I were in primary school, I would be just, I'd be begging my parents to stay up and let me stay up until 11:30 tonight, just so that I could see my picture go up.
And you can see some of the drawings up on NASA's website, and they are just gorgeous.
That's brilliant. That's brilliant.
Think about these children. I mean, some of these are 4 or 5-year-olds. They're coming into a world where we know what exoplanets are.
Yeah.
They know that there's more than 8, maybe 9 planets in the universe, right? They've grown up now with Kepler being a thing. And that's just a complete change in ideas from not very long ago.
Yeah, I mean, that's not a trivial statement. When I was at primary school hundreds of years ago, no, I mean, back in the 70s, early 80s, no. I mean, there was no discovery. There was no planet that we had seen outside of the solar system. And we still had 9, thank you.
And now a 4-year-old can tell you what an exoplanet is.
That's awesome. And it also makes me feel really old.
But yeah, the progress of science is amazing, and TESS is only going to contribute more to that, I think.
I mean, we were talking before about the sheer amount of data that TESS is going to be collecting. There's going to be data for those kids to be collecting to be sorting through when they're doing their PhDs in about 10, 15 years time. There's still going to be plenty of them to look at. So
it'll be old-fashioned by then, though.
Yeah, well, it'll be retro, old school. Hang in there, kids. It's all going to work out. So, I mean, those kids have got their exoplanet pictures going up on a card on this particular satellite. What's going to be the next launch that's going to inspire the next group of primary school kids and school children?
Well, one of the big ideas that TESS is going to provide groundwork for is, of course, the James Webb Space Telescope.
Now that's a good one.
Yeah. So it's been so long for James Webb, but it is totally going to be worth it.
Because when was it supposed to go up? The James Webb?
The original time, it was a few years ago.
Yeah, it's a couple of years over, and then it's been delayed again, hasn't it?
Yeah.
So tell us a little bit about the James Webb, because it's really interesting in terms of not just its science, but also its orbit.
Yeah. Well, so James Webb is kind of the next grand telescope. TESS is a kind of a middle-size telescope. Kepler was one of the big ones. So you can sort of see that you have different types of telescope to do different functions. James Webb is mega, actually. It's the next Hubble, really.
Hence the delays. I mean, this is hard stuff.
Yeah, and you absolutely got to get it right.
Yeah.
James Webb is mostly looking towards the infrared part of the spectrum. So again, it's really going to target these cooler stars, and it's going to have detectors on board that can do some of the science that we've talked about, like atmospheres, for example, as well as get much, much more information about the host star, the environment, the planets that we're going to find as well as a whole host of other science goals as well.
So it's a telescope on a grand scale, a little bit like Hubble?
Yes, it's definitely that sort of scale. Well, it's actually going to be bigger than
Yeah.
Hubble. The mirror is much bigger. It's nearly twice the size. And the heat shields on it are the size of a tennis court.
We make fun a little bit of our poor old James Webb is so delayed. But no, fair enough. You know, this is hard work. One of the other really interesting things about it, from a physics point of view, is that it's on a really interesting orbit. Like, its orbit is not just, circling around the Earth. It's out there in a very special kind of orbit called a Laplace point. Hi. Sorry, little interlude here from the editing booth. I just said that the James Webb Space Telescope will orbit in a position known as a Laplace point. I actually meant Lagrange point. Lagrange, not Laplace. Apologies to mathematicians and astronomers everywhere, okay? Right, back to the show. What kind of orbit called a Laplace point?
Yeah. So it's going out to the same place that we put Herschel, for example, which was actually another infrared telescope. It's called L2. And it's basically a special orbit where it will follow the Earth around in its orbit, but it will be slightly further out than Earth. So it's not going to crash into us. It's just a nice, quiet place that we've kind of filled up with telescopes actually now.
But it's a special place because if you work out the gravity of the system, of the telescope and the Earth and the sun, and I can't remember, does the moon come into it? I don't remember.
Jupiter, everyone wants to.
Then this is a particular point where if you just put something there, it'll quite happily stay there in a really nice stable spot, following the Earth around in its orbit for a very long period of time. And it's not sort of whipping around the Earth like the moon does or like most of our satellites do. It's just this little calm little backwater of space that happens to be gravitationally pretty special. Go and look it up. It's really, really interesting if you're into that kind of thing. So do we currently know when James Webb's supposed to go up?
I think they're projecting 2020.
2020. So we'll be on episode about 112 by then. But we could do a live one on James Webb going up. That'd be fun.
Yeah, that's good. It is, and you have to always thinking about what's the next step. I mean, science is progressive, but you have to kind of know a little bit where you're going, because we have to know now how to develop the instruments for, say, these primary school children that are going to be scientists in a decade or 2 decades' time.
So that's it for this week. If you've enjoyed the episode, you could really help us out by leaving a review and a rating on your podcast directory of choice. You can probably do that within the app you're using to listen to us right now, actually. And if you want to contact us, Emily, how can they go about reaching us here at Syzygy headquarters?
Well, we're on Twitter, so you can look us up at Syzygy Pod. We also have a lovely website, which is syzygy.fm.
Nice. Yeah, and remembering SYZYGY.
Yep, spelling is important.
The show is produced by me, Chris Stewart, and co-hosted by Dr Emily Brunsden from the University of York's Department of Physics. But we should probably go and get ready to tune into NASA TV tonight. So we'll catch you next time with a bit of a TESS update. It'll either be all thumbs up and very excited, or Emily will be pouting a little bit. We'll just have to see. So keep your fingers and toes and everything else crossed, everyone. But until next time, it's bye for now.
See you later.
Hello and welcome to another episode of Syzygy. I'm Chris Stewart, and joining me at the microphone, as ever, is University of York astronomer, Dr. That's the doctor.
I'm not
Doctor?
usually called that.
You're not a doctor. It's the doctor effect.
It's a Lagrangian point, not a Laplace point.
Oh, did I say Laplace? Damn it. I knew it was a last something. You're right, Lagrange. Well, I might just have to sneak in a quick overdub of that one. Goose, what an idiot. Oh well.